Hello, George Notchik here. The other day I was asked how might I go about integrating this particular function where we're taking the integral from 0 to x on the integrand e to the minus t squared with respect to t. Now if the exponent here was just t and not t squared, this would be a trivial integration where the integral would just be the integrand itself, e to the t. But the fact that it's t squared greatly complicates this particular problem. Now, this integral is related to a special function called the error function, which I'll talk about at the end of the video. Now, this function cannot be integrated in closed form in terms of elementary functions in general. But one can get it by taking the infinite series, power series expression, the Maclaurin series, and integrating it term by term, and I'll give the result later on that also. But the fact that this cannot be integrated in closed form in terms of elementary functions means that when we talk about elementary functions, elementary functions are those functions of a single variable which is a composition of a finite number of arithmetic operations, exponentials, logarithms, constants, and any solution to algebraic equations. Elementary functions include things such as trigonometric and hyperbolic functions and their inverses, because these types of functions are expressible as exponentials with complex exponents and complex logarithms. In this scope of talking about elementary functions, we include that the variables and constants can be elements of the complex numbers of the form, you know, a plus ib, where I is the square root of minus 1, the imaginary constant. So basically all trig functions and hyperbolic functions can be expressible as exponentials. An exponential is a very basic function, and even though we recognize trig functions and hyperbolics and as having special symbol notation, they can also be expressed in terms of exponentials. The exponential is very basic and it encompasses a very wide range of functions, because a wide number of functions can be expressible as exponentials. So if we can handle exponentials, we can handle trig functions, hyperbolics, and many other types of non-algebraic expressions. Now I'm going to go ahead and show that there is one case in which this particular function can be integrated, and I came up with a way of doing it, and it uses a number of different techniques of integration, which I found kind of interesting, and you may find interesting too. Now, what I'm going to do is look at this integral where our upper limit, we're going to take our upper limit as infinity. It's an improper integral. So we're going to look at e to the minus t squared dt. And let's say this is going to have a very definite value called a, because our limits are no longer variable or non-specific. We actually have well-defined boundaries on this particular integral, even though it's an improper integral. The integral can be evaluated in closed form. Now I'm going to do a trick here. And what I'm going to do is, since a, we've defined a as being this integral, I'm going to look at a squared. And I'm going to express a squared this way. So we've got a squared is the integral from 0 to infinity e to the minus x squared dx times the integral 0 to infinity of e to the minus y squared dy. Each one of these integrals is a, so this product is a squared. Now, since the integration with respect to x and y are independent, and there are no y's in this integral and no x variables in this one, I can combine these integrals into a double integral. I'll go from 0 to infinity of e to the minus x squared plus y squared dx dy. And using property of exponents, the product of an exponential is just the exponential with the sum of the exponents. Now I'm going to make a variable substitution here. I'm going to call x squared plus y squared equals r squared. I'm going to convert over to polar coordinates. I'm going to use a polar coordinate system. And when we do that, if we look at how we're integrating in the xy plane in the polar coordinate plane, we're integrating x and y from 0 to infinity, which means we're integrating in the first quadrant. So we're integrating all in the first quadrant, and if we look up at our differential element of area, dx by dy, it's just this little differential area here, which has dimensions dx and dy on a side. Now when we go over to polar coordinates, our r variable, radial variable, goes from the origin on out in the radial direction, and our theta direction is a rotation. Because being complete here, if we go into polar coordinates, the x becomes r cosine theta, y becomes r sine theta. And we can see that here. If this is theta, then the x value is just the projection of the radial vector down onto the x-axis, so it's the hypotenuse, which is r times the cosine of theta, and the y, if we go here, this y is r times the sine of theta. Now if we look at our differential element of area in polar coordinates, one side is differential r. That's the length of that side if we take a differential r. And on this side, it is the arc length defined by theta, so this is r d theta. We take the radial direction r and rotate it through theta, and that gives us, if we rotate it through a differential theta, say here d theta, then this side length is the radial direction out times d theta. So now we can express our differential area. I'll call differential area is dx dy, which is also r dr d theta. This is in the Cartesian coordinates, this is in polar coordinates. So now I can rewrite this integral. This is the double integral of e to the x minus x squared plus y squared, which is r squared, so it's e to the minus r squared, and then the differential area is r dr d theta. Now, since I've changed coordinate systems, I also have to redefine the limits on my integral. In the xy plane, I'm sweeping out the first quadrant by taking x from 0 to infinity and y 0 to infinity, and that sweeps out the first quadrant. Now in polar coordinates, to sweep out the first quadrant, the area in the first quadrant, the radial vector, or the r variable, goes from 0 on out to infinity as I sweep the radial line from 0 through theta to pi over 2. So theta goes from 0 to pi over 2 as r is going from 0 to infinity, and that sweeps out the first quadrant in that manner. So the limits on the integral now becomes, on the theta, which is the outer integral, we go from 0 to pi over 2, and on the r variable we go from 0 to infinity. Now we can integrate out the d theta to begin with, because it does not appear in the inner part of the integrand. So we can write this now. Integrating out d theta, we get pi over 2 times the integral from 0 to infinity e to the minus r squared r dr. I've just integrated out the theta. Now we do a change of variable here in order to integrate this further. So I'm going to make a variable substitution. I'm going to make u is equal to minus r squared. So then differential u is equal to minus 2r dr, taking the differentials on both sides. Now we can see that we end up with an r dr here, which is the same here. So this simplifies the integral considerably. So now we go with the integral e to the minus r squared. I'm going to substitute in u for r squared. So we have e to the u. And then r dr is just du over minus 2. Just solving this for r dr. R dr is equal to du over minus 2. And that's what we have here. And we have a pi over 2 in front. I'll bring the minus 2 out. So we have minus pi over 4, the integral of e to the u du. Now, we have to get the new limits. Well, when r is 0, u is 0. See, here we have r is equal to 0. So in that case, u will be 0. But when r goes to infinity, u goes to minus infinity. Minus infinity squared is still just a minus infinity. So we go 0 to minus infinity. Well, this integral we recognize as being very simple. The integral of an exponential is just an exponential. So we write this now as minus pi over 4 e to the u evaluated between 0 and minus pi, or minus infinity. Well, this evaluation, I will go up here again, this is equal to a squared. So then a squared is equal to minus pi over 4 e to the u between 0 and minus infinity. So evaluating this, we have minus pi over 4 times e to u at minus infinity is e to the minus infinity minus e to the 0. Well, e to the minus infinity just goes to 0, and e to the 0 is 1. So this becomes a positive pi over 4. And that's a squared. So a then will just be the square root of both sides, where a is equal to the square root of pi over 2. And that's the answer. That's the answer for this integral here. This integral is equal to the square root of pi over 2. To recap, we started out with this function defined on the interval 0 to x of e to the minus t squared with respect to t, and we found that if we took the limit of this function as x goes to infinity, the upper limit x now becomes infinity, so this integral looks like this one, and we found that its value is the square root of pi over 2. So the limit of cap f of x as x goes to infinity is the square root of pi over 2. And what this is the area under the e to the minus t squared function. So if I were to plot this particular function out, e to the minus t squared, in this direction, if this value is 1, my y value is here, and when t is 0, e to the 0 is 1, so this function decreases rather rapidly. And what this integral represents, of course, is the area under the curve of e to the minus t squared between the t-axis and the function. And if we let t go out to infinity, all the area under this curve out to infinity is the square root of pi over 2. Now, I also mentioned that if we have a variable limit x, say we want to find the area under the curve from 0 to x, this amount here, there isn't any way we can express that in terms of elementary functions. So we have to find another way to compute this. We can do it numerically or find some other expressions in terms of power series. Well, this particular integral shows up often enough in probability, statistics, and partial differential equations having to do with the diffusion process that we've given a variation of this a special name. It's a special function which we call the error function. We define ERF on x, which is the normalized version of this particular integral. It is 1 over the square root of pi from minus x to x of e to the minus t squared dt. So we see that we have this integral here, or we can write it in a little different form, is twice pi over 2 from 0 to x of e to the minus t squared dt. And we see that this is this integral with a scale factor 2 over the square root of pi. And why that is done is so that when the error function as x goes to infinity, this becomes equal to 1. This particular part of the integral is square root of pi over 2. We multiply by 2 over square root of pi. So the limit on the error function of x as x goes to infinity is equal to 1. The error function is a tabulated function because we cannot express it in terms of elementary functions. A lot of special functions are tabulated in that manner, like Bessel functions of the first and second kind, elliptic integrals. a number of these special functions show up in engineering science often enough that we've given these particular integrals special names, special function names. So if we were to plot the error function with x, what it looks like, this value is -1, this is +1, and this is the value of the error function, and it looks like this. It's an odd function, and that is because we can see that because the integrand is even. Even function means it's symmetrical about the y-axis. If I were to take minus t's in here, this function would be a mirror image of itself about the y-axis. It's an even function. And when you integrate an even function, you get an odd function. Odd function means it's reflected about the origin. So the error function looks like this. Like I said, it shows up quite a bit in engineering and mathematics. Now, to get the values here, one way we can do it, we can evaluate this integral, is to express the integrand, e to the minus t squared, in terms of a power series, the Maclaurin expansion of the integrand, and then integrate it term by term to get what the value of the integral is. So if we look at the integrand, or after doing all that, I can express the error function as 2 over the square root of pi, and I'll write it in compact form here. This is n equals 0 to infinity of -1 to the n power t raised to the 2n plus 1 over n factorial times 2n plus 1. And if I were to expand this out term by term, this will be 2 over the square root of pi times t minus t cubed over 3 plus t to the 5th over 10 minus t to the 7th over 42 plus t to the 9th over 216, and the next term will be minus, and this goes on forever. Now, because the error function is an odd function, we see that we end up with odd powers in the expansion. That's always true. That's what's characteristic of an odd function. An odd function has an expansion that involves odd powers, and if it was an even function like this, e to the minus t squared over 2, if I were to take the Maclaurin expansion, all the powers would be even. And when you integrate any function involving even powers, you get an odd power. For example, if I were to integrate t to the n with respect to t, in general it's t to the n plus 1 over n plus 1. So if n is even, n plus 1 is odd, and if n were odd, n plus 1 is even. So even functions integrate to odd functions integrate to even functions.